We're going to start talking about Newton's second law. Best way to go about this is to just give you Newton's second law in its mathematical form, because it is the result of what happens if things aren't balanced. So we've been talking about first law problems, and in every circumstance there, we've been talking about balance. If you apply a force that is unbalanced, we use the word net force. Net means just sum of all forces. So an unbalanced net force means that we are dealing with something that is not balanced. One of the forces is not balanced by another force anywhere. If it's unbalanced, then the object accelerates. It accelerates in the direction of the unbalanced force. So one of the first things I want you to have in your notes, because this comes up on the exam a lot, acceleration and net force always have to be in the same direction. Acceleration and net force always have to be in the same direction. Now, in your definition there, it may be helpful for some of you to put down there that net force doesn't mean a single force. It means the result of adding all the forces together. So you may not have a force that points in the direction of the acceleration, but the net force might. Everybody understand the distinction? So when we talk about net force, we're talking about the sum of all the forces. If it's unbalanced, the object accelerates. The acceleration and the net force are always in the same direction. Now, that gets us started here, but there's a problem with this, and that's something that I think requires a bit of conversation. If there's an unbalanced force, an object accelerates. How much it accelerates depends on a property of the object. Now, I know you know what this is. You know this is mass. But this is what's known as inertial mass. Because what we're really talking about here is the object's inertia. Newton's second law is often called the law of inertia. And the word inertia means an object's resistance to changes in motion. Now, that's what this law actually states. It's an inverse. It states that if I apply the same unbalanced force to two different objects, the one that accelerates the most is the one that has the least inertia. I know that's obvious. Bigger things are harder to move than smaller things. So if I push on two things, the one that moves the most must be the one with less inertia. The one that moves the least is the one with more inertia. But the definition of mass in this context is based on how it performs, which is probably the right way to define it. I tried to have a conversation in sixth period. It did not go well. When we talk about mass, and I've said this word before, mass is an intrinsic property. Can't really define it by what it is, but we can define it by what it does. So the first thing is mass has inertia. It has inertia. It resists changes in motion. I tried to ask the question about things in my room, which of the things in my room had mass. And I asked about Pickle Rick. I said, does Pickle Rick have mass? And somebody in the class said, yeah. And I go, how do you know? And they said, because it took up space. I said, that's not the right answer. Can't say that. How do you know it has mass? Well, you laugh, but therein lies the truth of the argument, right? It required a force to get it to move. Period. That defines something with mass. I mean, the fact that you can feel it means that gravity is pulling down on it. If you hold it in your hand, you have to apply a force up on it to keep it in place. That experience is how you know it has mass. An astronaut has to take his mass or her mass in space all the time. But there's no gravitational force to use there because they're falling the whole time. So how do they take their mass? Well, they give themselves a push and they measure their acceleration. They have a special chair for this that kind of shakes them. It applies a force on them and they measure the acceleration due to that force. And that's how they determine the mass of the astronaut. They have to take their mass every day to ensure that they're not losing bone density while they're in space. It happens all the time. If we're going to get to Mars, we're going to have to find a way to preserve bone density because astronauts are losing it the whole time they're in space. So one way to test whether something has mass is to see if it resists changes in motion. Give it a push, and then see if it resists that force. The second way is gravity. Does it create and does it respond to gravity? You know, it's kind of funny how we know things have gravity, or experience gravity. We know simple things like you can drop something in the room. And so that's easy. Do you know the experiment that was conducted to show that mass creates gravity? Cavendish is the name of the scientist who came up with the experiment. And I'll be honest, it's a pretty neat experiment. It's neat for a number of reasons. One, it was done hundreds of years ago. He was attempting to prove Newton's law of universal gravitation. He took two really large iron spheres and connected them by a metal rod that was able to support their mass. And he suspended it in the middle on a high tensile metal string. Then he put a mirror right here at the center and shone a flashlight right on the mirror so that the light would bounce off the mirror and strike the wall over here someplace. Then, and this is critical, this is what's really neat, he took two other spheres and he brought the two other spheres close. Just grabbed them and stop it. Stop it. Do my bidding. He brought the other two spheres close by. And when he did, the spheres rotated and the beam of light moved along the wall. And he pulled them back, the spheres moved back into their original position. He carefully measured these distances that he had them, he tried to be symmetrical. I'm not being perfectly symmetrical here. What's amazing is that he was able to measure the proportionality constant between the size of the force required to move the spheres and the masses of the spheres themselves. Now, the reason this is important is that proportionality constant shows up in an equation called Newton's law of universal gravitation. Newton just assumed this thing happened, and we're going to study this later. Cavendish measured the size of this value empirically. It had been guessed at based on the resolution of the Earth, the revolution of the Earth around the sun, but Cavendish was able to measure it directly. The value he measured hundreds of years ago, we still use today. That's how good this experiment was. But what's really awesome about this experiment is that it was the first experiment to lend an incredible amount of evidence that objects that have mass create a gravitational field and can affect other objects with mass. He did it in a room about this size, painstakingly careful measurements, as you can probably imagine. Today you can do it, you can buy apparatus that will do this experiment with lasers and stuff, but we still don't get much better value for G than he got hundreds of years ago in basically a barn out in the middle of some field. Pretty amazing experiment. So, back to work here. Newton's second law. what we are going to do with Newton's second law isn't much different than what we do with Newton's first law. It just adds the idea that an object can be accelerating now. So now we're going to talk about how we can cause an object to change its motion. Start an object into motion, stop an object from moving, change an object's direction. That's what this tells us we can do. For all the prior work we've been doing, we've been saying that the net force is equal to 0. So we've been talking about situations in which the state of motion isn't going to change. But now the state of motion can change. It affects only one thing in our procedure, right? If you go through your whole procedure, the only thing that it affects, really, is at one point or another, we've been saying, well, I'm going to draw a coordinate system, and I want to draw that coordinate system so that it lines up with as many forces as possible or is aligned with the direction of the acceleration. Well, we've never had to use the first priority before. Well, now we will. That's really the only change in your procedure, and the fact that you have to choose whether it's a first law or second law problem. Let's try it in practice. I have a stupid, simple practice problem. But a good place to start. I have a frictionless surface. I have a box that's at rest on that frictionless surface, and I want to give it a pull. The box has a initial velocity of 0. It's at rest on the surface. I would like to know how long until the box has traveled a displacement of 15 meters. Now, the first thing I want to throw at you is that this problem sounds grossly different than what you've been doing so far. Would you agree? It sounds like what we did first semester, or the first unit. But we're studying forces now. So all the stuff that's been given here isn't about acceleration, it's about forces. But I need to remind you that the force concept model can only do two things. It can either tell you the size of a single force or group of forces, or it can tell you the acceleration. That's the only thing the force concept model can do. We've spent all of our time talking about the size of an individual force. That's all we've done for the last 2.5 weeks. But now we could do this. If we had the acceleration, would that be enough information to figure out the displacement? It would be. So we're going to apply the force concept model to this arrangement to see if we can use it to find an acceleration. Now, everything we've already learned is directly applicable here. There's nothing new. You draw a free body diagram, which means I'm going to draw a normal force down. I'm going to draw that applied force at an angle. I'm going to draw, the weight down. An applied force at an angle and a normal force up. There. Sorry. It's clearly unbalanced, isn't it? By me saying there's no friction, I kind of made it very clearly unbalanced. So I'm going to draw a coordinate system, and I'm purposely drawing it lined up in the direction of the acceleration. So I'm going to make that my positive x direction. I'll make that my positive y direction. I have one force that needs to be resolved into components. So I'm going to have this one, which is 20 cosine 30 degrees, and this one, which was 20 sine 30 degrees. I'm back to my part where I apply Newton's laws, but now we have a problem, or we have a change. This is the second law problem. I want you to hear this very closely. The reason why we align our acceleration with only one direction is so that we can state that one of these is equal to 0 and the other one is equal to ma. It makes it possible for us to solve the problem. If we don't do that, then both of these have to be equal to ma in the x direction and ma in the y direction. That makes these problems infinitely more complex. And I use that word infinitely, not exaggerating. They become very complex. So we will always do everything in our power to align an accelerated problem in the direction of with the acceleration. I don't think you have the math to do it otherwise. So we've made it so that the x direction takes the acceleration and the y direction is 0. Now, everything else kind of remains the same. Normal plus 20 sine 30 minus 100 equals 0. This is mg. This is f sine 30. Right, all the things. Over here, of course, we just have 20 cosine 30 equals ma. Any question where any of these things came from? Do you see that it's the same kind of steps we've done so far? I'll remind you that the force concept model only can generate a relationship that maybe you can use to solve the problem. It generates one relationship for each direction. We've generated our two relationships. We can find the normal force, it's 90. Not particularly useful if I'm trying to figure out, how long it takes the object to go 15 meters. However, I can find the acceleration. Isn't it 1.7? I think that will help us solve our problem here. Force concept model can either give you a force or an acceleration. You might be able to use that to find something else. But this is what the change is now that we had second law. Not terrible? Try something else? Let's see if I can, I'm gonna make another easy-ish one. You got a box zipping along at 5 meters per second on a slick portion of the ground that has no coefficient of friction, hits a spot that has a coefficient of friction of 0.3. The section is 10 meters long. Does the object stop? Or does the object emerge at a slower speed? If so, what is that speed? Everybody got the question? All right, so I'll say it again. Got an object zipping along at 5 meters per second, hits a section of gravel or something that has a coefficient of friction of 0.3, lasts for 10 meters. Does that stop the object? Or does the object emerge at some slower velocity? If so, what is that velocity? I am hearing a kinematics question. Are you hearing it? I've got an initial velocity of 5, possible displacement of 10. I say possible. We don't know if it does. A possible final velocity of 0. Ooh, we don't know. But I do know one thing. If I could just get an acceleration, I could probably figure some stuff out. Right? So I think we can get the acceleration from what's here. Do you think you can? All right, so let's worry about the kinematics problem later. Let's recognize that getting an acceleration gets us one more of the 3 things we have to solve the problem. Let's give it a shot. I see 3 forces acting on my box. Do you see 3 forces acting on your box? Does anybody have a downward force? When I asked that in 6th period, people looked around to see if anybody else was saying yes. I found that to be weird. Right? Isn't there always a downward arrow? Except for unless we're looking down on the object. Yeah. This one's easy. In fact, it's 20. Right? MG is 20. Is there an upward arrow? Yeah, I think so. And look, I know we're supposed to do this as a process, and I have a process that we can do, but isn't the upward arrow going to be the normal force? Isn't it also isn't it also 20? Yeah. It's got to be balanced up and down. So, you can skip steps if you're able to. I'm able to, and some of you are able to. There has to be balanced up and down. I'm going to leave it as N right now, but start looking at ways to start skipping through some things if you can. When that box hits that patch, though, there's going to be friction. And friction has to act to the left to slow the object down. Set up coordinate system. Do my best to line up that coordinate system with the direction of the acceleration. Something like that. Negative y, positive x, negative x. And be careful here, but I've just labeled x and y. We all good? Net force in the x direction, net force in the y direction. Which one is 0 and which one's MA? All right. There's only one force in the x direction, friction, it equals MA. 2 forces in the y direction, though, normal equals 20. So force concept model got me this far. That's not enough. I need to bring something else here. Do we know anything else that we can bring to bear on this problem? What's that? How do I bring that to bear here? So I will bring in my equation for friction, which joins together the normal force and the frictional force. And that'll be 0.3 times 20, or 6 newtons. All right. Pretty straightforward, isn't it? I've got 6 newtons equals 2 kilograms times A. So A equals 3 meters per second squared. Not terrible. Be careful, though. I made a mistake. And I want to make sure we see the mistake I made. I made to the right positive. The direction of the force was negative. I probably should have put a negative sign here, right? The reason I'm bringing it up is because, is this acceleration going to speed up the object or slow down the object? We need to be aware of direction. If I had made this side positive, this side negative and this side positive, I'd have to be careful about this velocity. What I want to impress upon you is that when we make this statement of what's positive and what's negative, we are making it for the whole problem. Since the 5 was positive, I made the direction the box was going positive. But my acceleration is negative. It's in the direction of the unbalanced force. So I need to be aware of direction.